All right, I think it's 9:30 on the dot, so we'll get started. Thank you very much for inviting me, and I'm really excited to be here. So, as my title says, the topic of the lectures that I'll be giving is sort of adventures in public key cryptanalysis. And the plan for my 3 lectures, you're stuck with me for 4 hours here. So part 1 is sort of introduction and factoring, and the big questions that we'll be looking at is what is public key crypto actually based on, and how you can break RSA from the comfort of your very own home. Part 2 is talking about the paper you just heard about generating keys, and in particular how not to generate your crypto keys. And how many people who should know better have screwed it up in practice. And part 3 is all about breaking keys with lattices, and sort of the big theme here is how fragile is RSA to various kinds of difficulties in usage, and why not to post your private keys to pastebin. So I will launch right in here. So this is something that you probably see very often if you go online. We visited Google, and our connection is encrypted with HTTPS. And if we look at what Google is doing on our behalf, the browser will tell us a lot of information about the crypto that it's using. In particular, it says that it's using elliptic curve Diffie-Hellman as part of securing our connection. So, of course, the Diffie-Hellman scheme was sort of the founding paper in public key cryptography. So this is a picture of Merkle and Hellman and Diffie from a very long time ago. So this paper, New Directions in Cryptography, introduced the first scheme for 2 parties to agree on a secret key using only messages that could be sent in public. Hopefully we've all seen this before, so this is only review. But the way that the Diffie-Hellman scheme works is you have some public parameters, you have some group G, which can be, say, integers mod sum prime P, or an elliptic curve, or any other group you want to work over, and you have some generator of this group. And so if Alice wants to communicate with Bob, what Alice does is send G to the A to Bob, and Bob sends G to the B to Alice, and then Alice and Bob can each compute G to the AB easily. But an adversary who's sitting in the middle and watching their connection shouldn't be able to compute G to the AB just from viewing the messages G to the A and G to the B. And of course, what computational problem is this based off of? Sort of the most basic underlying problem is the problem of computing a discrete log. So that's if you are given some element G to the A in whatever group we're working over, computing the discrete log is the problem of computing this A. And solving this problem would permit an attacker to compute the shared key by viewing the messages, computing, say, A from G to the A, and then raising G to the B to the A power. And discrete log is most likely not NP complete unless something very surprising happens. So, of course, this is not the exact problem that we were talking about. The exact problem that we were talking about in the Diffie-Hellman scheme is the problem of given G to the A and G to the B, computing G to the AB. And this is exactly the problem of computing the shared key from the public information. And this reduces to discrete log in some cases, but in general, the security of schemes based off of Diffie-Hellman, their hardness is based off of a Diffie-Hellman assumption, which is that the problem of computing G to the A and G to the B, or G to the AB from G to the A and G to the B is hard. So, okay. So much for Diffie-Hellman. We will move along. So the next example of a very, very commonly used public key crypto system is RSA, which if you ever look at your browser certificates is almost certainly the encryption and signature algorithm that's being used. So of course RSA was sort of the second most influential paper in public key cryptography. This is also a very old picture of Shamir and Rivest and Edelman. And just to review the RSA scheme very briefly, in the RSA scheme we have a public key which is the product of two large primes P and Q, and P and Q are the private key. The public key also has an encryption exponent E, and the private key is the decryption exponent D, which is E inverse mod phi of n, so E inverse mod P minus 1 Q minus 1. And so if Alice wants to send a message to Bob again, she asks for Bob's public key, which is the pair N and E. And she encrypts her message by raising it to the eth power mod n and sending it to Bob. And then Bob can decrypt the message by, or decrypt the message by raising the ciphertext to the dth power mod n. So this is the textbook RSA that hopefully you saw at some point in at least your undergraduate careers. So RSA is also very commonly used for signing messages. So the way that this works is that if Alice wants to sign a message for Bob, she sends her public key N and E to Bob, and then she can sign a message by raising it to the dth power mod n, so raising it to her decryption exponent, her private key mod n, and then Bob, using her public key, can raise the signature to the eth power and verify that the signature is a valid signature of the message. So what computational problems is RSA supposedly based off of? One problem is factoring. So given n, compute its prime factors. This would be if you get n, you want to compute the prime factors p and q. This is computationally equivalent to computing the private decryption exponent d. And factoring, again, is unlikely to be NP complete unless something very surprising happens. The RSA problem exactly is what you need to break RSA would be to be able to compute eth roots mod n. So this problem is given n and e and a ciphertext, compute some x such that x to the e is equal to c mod n. This is exactly the problem of decrypting an RSA encrypted ciphertext from only public information. This is also equivalent to selective forgery of RSA signatures. And it is unknown whether this reduces to factoring or not after 35 years. It is, I guess I shouldn't use the word conflicting here, but there are results suggesting possibilities either way, depending on what kind of computational model you use. So this is the most commonly used public key crypto system, and we have no idea. And so when we talk about crypto systems that are based off of RSA, generally they have some form of computational or decisional RSA assumption, which says that this problem of computing eth roots mod n is hard. So at this point, I just want to have a brief public service announcement. I may have shown you something that looks like a sort of prescription for how to do RSA, and I want to say that you do not do RSA this way, and you do not implement RSA this way, because textbook RSA is completely insecure. And one of the major reasons is that RSA encryption is homomorphic under multiplication. So if you don't have any padding or any modification of your message, then an attacker can do all sorts of fun things with the scheme. For example, given some ciphertext C, which is your message to the eth power mod n, an attacker can construct any message they want of the form C times a to the e mod n, which is a valid encryption of m times a for any a they want. An attacker can similarly, if you're looking at this from the perspective of signatures, given okay, I guess for chosen ciphertext attack, an attacker can, given some ciphertext, ask for a decryption of the valid message C times a to the e, and get back a c to the a, or c times a, which they can then divide by a and get the original message back out again. So if you're in some model where attackers can ask for decryptions of messages that have been encrypted, then they may be able to break the scheme. For signatures, an attacker could convince a signer to sign what looks like an innocuous looking message, say z equals x, y to the e mod n, and then they can compute a valid signature of x just by dividing by y after they get the signature. So in practice, you always, always, always use padding when you're using RSA. And you probably shouldn't be implementing RSA yourself anyway, unless you really know what you're doing. Some people in this room really know what they're doing. So, the last scheme that I want to talk about is the digital signature algorithm, which is the US federal standard digital signature algorithm. So the way that DSA works, it's much more complicated than the other two, but the main underlying problem here, it's still based off of discrete logs. So your private key is some x, and your public key is a bunch of sort of domain parameters, and then you have some value which is g to the x mod p. So we're working in a group P which has some special properties. And in order to generate a signature, the signatures are randomized. You basically generate a public nonce here by you generate some random k, and then you take g to the k, which is one part of your signature, and then you generate your signature using this value k, and if you feel like it, you can verify that this actually works. So DSA is actually equivalent to discrete logs, at least in the random oracle model. So I guess that's the benefit of its structure. So this is a crypto talk. So I wanted to, it's important to have at least one XKCD cartoon in any talk about computer science. So since we're talking about public key encryption, here is the most appropriate XKCD I could find. So we have a crypto nerd's imagination. His laptop's encrypted. Let's build $1 million cluster to crack it. No good, it's 4096-bit RSA. And then, of course, blast, our evil plan is foiled. And what would actually happen, well, his laptop's encrypted. Drug him and hit him with this $5 wrench until he tells us the password. Got it. Okay. The rest of this lecture will be talking about the first part of this, this cartoon. What is this actually feasible, and how you can do it yourself? And well, what about the second part of this this slide? Well, this is not really ethical research. So since we're academics, I'm going to skip over this part. Well, so what might actually happen in practice? Well, maybe an attacker would install a keylogger on his laptop and steal his password. Maybe an attacker would find a software vulnerability and just pwn the laptop. Maybe the attacker would look for implementation flaws that result in weakened crypto. And so this is what I'm going to talk about in the other two lectures. So as promised, the rest of this lecture is going to be about factoring and computing discrete logs the hard way. And some of this material, I've given some joint talks with Dan Bernstein and Tanya Lange on the subject, so I have borrowed liberally from them. In this and in the next two lectures, I'm going to give some working code examples, and I'm going to give examples in Sage, which is free open source mathematics software. It's based off of Python, so it should look generally familiar if you're familiar with Python. And I think Sage is really great. It's kind of a mess, but it's also really excellent if you want to play around with sort of number theory computations. It's familiar, it looks like Python, it has a nice interpreter, you can do whatever you want, but it also hooks into a bunch of the best computational number theory libraries out there. So since it looks like Python, it's familiar, we can do whatever we want. 2 times 3 equals 6. One difference here is that the caret is exponentiation and not XOR. So whenever you see a caret, treat that as exponentiation. And as I said, Sage has a lot of useful libraries. For example, we can ask it to factor the number 15, and it tells us the correct answer, 3 times 5. It can also do slightly more sophisticated things. For example, if I ask it to factor a polynomial, it will also do that for me. So just to practice what we've been talking about and get a little bit more familiar with me throwing up a bunch of Sage code on the screen, this is what textbook RSA might look like if I implemented it in Sage. So I have, in order to generate my public key, I generate 2 random primes of size 2 to the 512. So that's a 1024-bit RSA key. I produce n by multiplying together p times q, and I choose my exponent e, which is 65537. This is the most commonly used encryption exponent on the internet. And in order to compute d, my private key, the decryption exponent, I take e inverse mod p minus 1 times q minus 1. So then if I want to encrypt a message, and my message here is hello world, and I have a stupid encoding here just to make it an integer, ignore that part. So my message, I raise it to the 65537th power mod n, and I get out a ciphertext. And then if I want to decrypt this message, I can raise the ciphertext to the dth power mod n and sort of decode my encoding, and I get back my original message. So yay, RSA works, even in Python. So at this point, I want to ask the question, how hard is factoring? So we saw this factor function that Sage had. How long do people think this takes on this computer? Any guesses? A second? 0.01 seconds. Okay, how long do people think this takes? So this is a 128-bit RSA modulus. 2 minutes? 0.1 seconds. How long do people think that this takes? Any guesses? 5 seconds? Very good. All right, how long do people think this takes? So this is a 256-bit RSA modulus.
1 minute.
Well, it's a little bit more than 1 minute. So this is the point at which maybe factoring starts to get a little bit iffy if I'm doing this like on battery power on my laptop on the airplane. What is this software actually doing on my behalf? What does modern factoring look like on a computer? Well, it turns out there's sort of, at least morally, 2 kinds of factoring algorithms. There's algorithms that have running time dependent on the size of the factor. And these are good for factoring very small numbers and for finding small factors of big numbers. And there's also general purpose algorithms that depend sort of only on the size of the number to be factored. And these are sort of the state-of-the-art algorithms that you would use if you want to factor a really big RSA modulus. So, of course, the most simple possible factoring algorithm you can think of is trial division. Just run through all of the primes up to your number and try dividing by each of those primes. And well, if you find one that successfully divides your number, you have at least found a factor. And trial division takes p over log p divisions in order to find a factor p. This is because there's about p over log p primes of size less than p. Okay. So we can do better than this. The Pollard-Rowe algorithm is good for finding slightly larger prime factors than trial division. The intuition behind this algorithm is that you want to take a random walk among elements working mod n, And if p divides n, then there will be a cycle of length p somewhere in your random walk. And the details of this is that you expect to find, if you're taking a truly random walk, you expect to find a collision after searching about square root of p random elements. This is because of the birthday paradox. In addition, well, so you could do this by sort of storing every single, how are you going to find a cycle when you're taking this random walk? You could store every element that you look at and then search through each element in order to find whether you have now found a collision. But instead, the algorithm does much better by using Floyd's cycle finding algorithm, which requires constant memory. You store 2 pointers, and you move one pointer twice as fast as the other until they coincide. So this takes the same amount of time and constant memory. Why is this called the row algorithm? This is sort of a picture of what the random walk sequence might look like, that you have some cycles and you start at random points until you find a cycle. And here is the path that the algorithm might take. And if you squint your eyes and turn your head, it kind of looks like a row. So that is why it's called the row algorithm. So what does this look like in Python? So I define my random function that I'm going to use to iterate as I'm going to take some element and map it to like x squared plus c mod n. And I'm going to just choose some random values for my starting point and my c. And then I'm going to keep my 2 pointers, a1 and a2, and I'm going to start at f of a and f of a. And then until I find a non-trivial common divisor, I'm just going to iterate my pointers. I'm going to take a1 maps to f of a1 and a2 maps to f of a2. And then I'm going to return the GCD of n and a2 minus a1 as soon as I get something that's actually interesting. So if I input this rather long number and I call row of n, I get back the factor 2053. And this is basically immediate. So good little algorithm, very simple. Pollard, I guess, was very busy finding interesting factoring algorithms. So he's also responsible for another very important factoring algorithm for finding small factors. This is the Pollard p-1 method. So the intuition behind this method is that if we can find some element a to the r which equals 1 mod p, then p will divide the GCD of a to the r minus 1 and n. Straightforward. Of course, since we're trying to factor and we don't actually know what p is, but we can choose some very, very smooth number r, where smooth means that r only has very small prime factors. And we can hope that the order of a mod p divides this number. This will be the case if the order of a mod p only has very small prime factors. So here's an example of doing this. I have my very large number n, and I choose r to be the least common multiple of this very large range. This is a slow computation, but it only needs to be done once for all of the numbers that you're trying to factor this way. Then I take, I start with, I take some, well, I guess a is 2 here, and I raise 2 to the r minus 1, and I compute the GCD of 2 to the r, 2 to the r minus 1 and n. And this is fast, and this gives me a rather larger factor of n. So this method will find larger factors than the row method, but in the same amount of time. But it only works for special primes. And it only works for special primes where p-1 has only very small prime factors. So in the previous example, p-1 has this factorization. And as I said before, it's smooth. And if you look at a lot of crypto standards, they require using only what they call strong primes, and these are primes where p-1 is not smooth. And that is exactly in order to protect against this factoring algorithm. But of course, at this point, this recommendation is outdated because this is not the state of the art in factoring algorithms. The elliptic curve method, which I will present on the very next slide, works against even strong primes. So it is something of a waste of time to try to protect against this. The last sort of small prime, well, not small prime, but sort of the last sort of generic good for all sizes of primes algorithm that I want to present is the elliptic curve method. This is good for finding medium-sized factors of numbers. And so the intuition here is that the p-1 method works in the multiplicative group of integers mod p. And the elliptic curve method is exactly the same algorithm, but it works over the group of points on an elliptic curve modulo p, which sounds kind of scary, but we're just essentially replacing one group for another. In this new group of elliptic curve points, multiplication of group elements becomes addition of points on the curve. And all of the arithmetic is still done modulo p, or modulo n. And the reason that the elliptic curve method is so effective is that the order of an elliptic curve modulo p is somewhere in this fairly large range of p plus 1 minus 2 root p and p plus 1 plus 2 root p. And there are lots and lots of smooth numbers in this interval. And so if one elliptic curve doesn't work, you can try more until you find a smooth order. So unlike the original p-1 method where we were stuck with this one group, and if p-1 happened not to be smooth, then the method wouldn't work. Here we can just keep trying elliptic curves, and at some point we will find one where p-1 happens to be smooth or have a smooth order. So if looking at elliptic curves is scary, as computer scientists, we don't actually need to think that much about the complicated math of the elliptic curves. So here's an example of how you might implement an elliptic curve in practice. So we can define just some Python class that will represent our curves. And I have it generating, this is to generate a point on an elliptic curve. And all I've done here is I've replaced the addition operation with this somewhat complicated set of equations. This defines an Edwards curve. And there are several different ways that you can define elliptic curves, but they basically, all they do is they give you some form of what the group operation looks like. And this is one of the possibilities. And so if I add 2 points, I just follow these rules. So if I define my elliptic curve class like this, then the elliptic curve method looks something like this, where I basically, sorry, I basically choose a point on my curve. I've chosen an arbitrary point here and some parameters for what my curve looks like. And then the actual algorithm looks exactly like the p-1 method that we just saw, where I take my point and I, well, instead of taking, before we were taking like a to the least common multiple of some very thing. Here I've replaced multiplication with addition, so I take p times the least common multiple of some big range of numbers, and then I return the GCD of essentially the x coordinate and n. And if I keep trying different curves, this will eventually work. The reason that this algorithm is so useful is that, among other things, it runs very well on GPUs. And so this means that if you want to, say, factor a very large number of generic integers, a very good way of doing this is to have a GPU farm, and you can have each one of these try an enormous number of different curves, and this means that the algorithm parallelizes very well and is very fast. This is still an active research area, And the elliptic curve method is the first sub-exponential time factoring method that we've seen. And it has running time L of 1/2, which is a notation often used in this area. Essentially, it means the running time is e to some constant square root of log p log log p. Are there any questions here? Or is everyone still asleep? Everyone's asleep. So,
Nadia will give some practical numbers later about the speed of this factoring algorithm.
I'll give one practical number. All right. Now we're going to move on to an entirely different set of factorization methods, which are sieving algorithms. I want to explain in depth the quadratic sieve and sort of the reasoning underlying the quadratic sieve has its roots in a very old factorization method known as Fermat factorization. So the main insight underlying Fermat factorization is that if we can find two squares that are equal to each other mod n, then a squared minus b squared is 0 mod n. We can factor that as a plus b and a minus b, and we can hope that one of a plus b or a minus b shares some non-trivial common factor with n. And so this means that, you know, your sort of first try at a factoring algorithm based off of this idea is to start at some numbers, say square root of n, and check c squared minus n, c plus 1 squared minus n, and so on. And at some point, we will find a square, something that reduces to a square mod n. And then we can use that to try to factor n. So this is Fermat factorization, which could take up to p steps. So this is not an efficient factoring algorithm. But the main insight underlying the quadratic sieve here is that we might not find a square outright as we're searching through each of these numbers, but essentially once we have enough factorizations, we can construct a square as a product of some of the numbers that we've looked through. This algorithm has essentially 3 steps. The first is, as before, we start at some point and we try to factor each of c squared minus n, c plus 1 squared minus n, and so on. And we will save these factorizations, but we'll only save a factorization if all of its prime factors are less than some bound. So if it is B smooth. And we will store each of these factorizations as its exponent vector. So we factored it. It's in the form, 2 times some exponent, 2 to the some exponent, 3 to the some exponent, up to b to some exponent. And if the product of some number of these di's is a square, then its exponent vector contains only even entries. And so this means that, so we've collected all of these factorizations of di's. If there's some product of them that produces a square, then we can look at the exponent vectors, and in multiplying, we are summing the exponent vectors. And that means that we want to find a sum of the exponent vectors that results in all even entries. And we can do this using linear algebra mod 2. So once we have enough relations, say more than the number of primes less than b, then we are guaranteed to find a linear independent or a linear dependence, and then it's just a matter of doing some linear algebra to find what this dependence is. And the last step is to compute square roots. We compute the square root of the number that we just calculated, and we hope for a non-trivial factorization. And it's a exercise for you that the square product has a 50% chance of factoring p times q. So here's a brief example of what this looks like. So we can try to factor the number n equals 2759. So of course the idea, if a squared minus n is a square, b sum b squared, then n equals a minus b times a plus b. So we'll start at, say, just above square root of n. So 53 squared minus 2759 is 50. That has an easy factorization, 2 times 5 squared. 54 squared reduces to something that doesn't seem to have very small factors. 55 squared doesn't seem to have very small factors. 56 squared doesn't seem to have very small factors. But 57 squared minus 2759, that has relatively small factors, 2 times 5 times 7 squared. 58 squared minus 2759, that also has relatively small factors, 5 times 11 squared. So the product of 50 times 490 times 605 is a square. It's 2 squared times 5 to the 4th times 7 squared times 11 squared. And so then the last stage of the quadratic sieve just computes the GCD of these numbers and gives us a non-trivial factor 31. The running time of this is dependent on how we choose this value b and how many numbers do we try to factor. And this depends on the probability that a randomly chosen number is b smooth. This probability is a heuristic estimate. So the running time of this and all of the future algorithms are heuristic. But the running time we get essentially the same as the elliptic curve method. So it's L of 1/2, which is e to the square root of log n log log n. The reason that I went over this in such detail is because I wanted to talk about the number field sieve, which is the state-of-the-art in factoring algorithms for very large numbers of the size of RSA moduli that we actually use in practice. So this has the best running time for general purpose factoring for very large numbers. And the main insight of the number field sieve is that we replace this relationship a squared equals b squared mod n with essentially a homomorphism between the ring of integers in some specially chosen number field and the integers mod n. And I guess we're an applied security audience, so number field might sound scary, but all you need to know is that it's a different mathematical structure that happens to have more primes in some sense. And so we only have to factor smaller numbers in order to find many small prime factorizations. But the algorithm looks essentially the same as what we saw before. It has the same kinds of steps. We've added one step in the beginning, which is polynomial selection, which essentially gives us, we're searching over different number fields, and we try to find a good choice of number field that will give us good factorizations. But the main steps are the same as before. There's a step of relation finding, which is to factor elements over our number field and over the integers. We do some linear algebra to find a square in our number field and a square in the integers. And then we take some square roots. Our square root in the number field we map into the integers, and then we hope that this will give us a factor. And this has an improved running time over the quadratic sieve of L of 1/3, so e to the log n log log n to the 1/3 with some constants that I've omitted here. There's been some really recent advances in the discrete log problem, which, as you remember, is computing L in g to the L equals t in some group. We care about this for Diffie-Hellman. And it's actually been sort of very interesting that for decades, progress in discrete log has closely followed progress in factoring. Even though the algorithms were slightly different, every time there was progress in either discrete log or factoring, you could somehow translate that progress into the other problem and get an equivalent improvement. And so the best running time for both discrete log and factoring was L of 1/3 using either the number field or function field sieve for discrete log. So the same as the best running time for factoring. And that is until this year, when a series of several papers, these are sort of the algorithmic papers that were released. There was this paper by Antoine Joux, a new index calculus algorithm with complexity L of 1/4 plus little o of 1 in very small characteristic. This appeared on the ePrint archive in February. And then much more recently, there was a follow-up, a quasi-polynomial time algorithm for discrete logarithm in finite fields of small characteristic. So this has running time like log n to the log n. And this is enormous news. This is the first asymptotic improvement in discrete log in decades. And this has also been followed by a number of papers that have just completely broken all sorts of different discrete log records in practice in various computations. The one detail that matters here is that these are for small characteristic fields, so not for, say, working mod large primes, for example, which is where we use Diffie-Hellman most often in practice. So I think this is the last serious math that I'll throw at you in this lecture. So how do these discrete log algorithms actually work? The main underlying idea, without any of the fancy improvements that actually give you the, say, L of 1/3 or L of 1/4 or L of 1 over log n or whatever, is just the basic index calculus. So remember, our goal is to solve g to the L equals, say, t mod p. And the algorithm works the same as before. We have a step which is relation finding. So we just start with a bunch of g to the r for lots of random choices of r, and we try to factor that. And we collect factorizations that are smooth. So g to the r is some p1 up through pk with exponents r1 through rk. And this will give us a relationship between the discrete logarithms of, say, r and, well, we can use r to get a congruence of discrete logarithms of p1 through pk, mod p minus 1. And then once we have enough relations, we can use linear algebra to solve for each of the log pi's. So at this point, we're almost done. The next to last step is to, well, we actually want to solve g to the L equals t mod p, and t might not actually be smooth mod p, but then we can just multiply by random elements g to the r until we hit on a smooth element. And at that point, we can then factor that as some new coefficients here. And once we've done this, then we can just write down what the discrete log of t is in terms of this capital R that we found here and the discrete logs of each of the primes and the exponents that we computed before. So this is how essentially all of the discrete log algorithms work. And so as I mentioned, the new discrete log algorithms have resulted in very impressive new computational results. But there's still a lot of work to do. Among other things, we need to verify whether the heuristic assumptions that these algorithms are using actually perform exactly as predicted in practice. And it's a big open problem. Do these results actually mean anything for discrete logs in large characteristics, so working mod p for some large prime, which is the case that we care about in practice for a lot of crypto systems that we actually use. And I honestly have no idea. I don't have a good understanding of these results, but this is sort of major news. And as I said before, most of the times that we've had some advance in either small characteristic or for discrete log, this is implied. This has been followed by an advance for large characteristic or factoring. And so the big question for me is, do these new results lead to any new insights about the problem of factoring? Because we're at the point where any new algorithmic improvements could potentially break some or all of the public key crypto that we use in practice. And the last time that we had a major new algorithmic improvement was in the early 90s, before we had the internet, where everyone was relying on RSA and Diffie-Hellman with fixed sets of parameters that were very difficult to change. And so if we have a new improvement that entirely changes those parameters, we have like billions of dollars of the economy and the security of every single computer on the internet that will be called into question.
So, Nadia, are there any
Yeah?
practical applications or standards that use the small characteristic load?
I'm not sure what standards use small characteristic. Does anybody know? I mean, certainly, like, it's relevant to understanding. I mean, I know that like other small characteristic fields are used for various applications. So I don't know if it's been used for discrete log standards in any case. I guess I should mention that one of the reasons that elliptic curve crypto is so exciting is that essentially, if you do, we can define elliptic curve Diffie-Hellman, which is it's based off of solving the discrete log problem over an elliptic curve group. And the reason that elliptic curve groups are so useful in this case is that all of these index calculus methods don't apply over elliptic curve groups. You can't do this trick where we sort of find all these small factorizations and use that to construct a solution. This is why the key sizes for elliptic curve crypto are so much smaller than the key sizes for doing crypto over the integers. So I want to sort of finish with a discussion about factoring in practice. So this is sort of a very brief history of some results in practical factorization. So around the time of the original development of RSA, Ron Rivest gave this sort of infamous estimate in a letter to Martin Gardner that factoring 125 digit, this is 125 decimal digits, number would require 40 quadrillion years. And in the RSA paper, it contains the estimate that an 80-digit N provides moderate security against an attack using current technology, and using 200 digits provides a margin of safety against future developments. Of course, I guess it's unclear what exactly a margin of safety means, but nevertheless, that was there. Now, of course, there was several big improvements in factoring algorithms through the 80s. In 1994, a group of number theorists factored the RSA 129 challenge, so that's 129 decimal digits that was contained in Martin Gardner's 1977 column. So this is larger than the 125-digit number that Rivest estimated would be impossible to factor ever. And in that paper, they say, we conclude that commonly used 512-bit RSA moduli are vulnerable to any organization prepared to spend a few $1 million and wait a few months. And progress in computing was such that 5 years later, a group containing some of the same people factored a 512-bit RSA key for the first time. So that's 155 decimal digits. They factored the RSA 155 challenge in 4 months of calendar time. And they have several estimates of how much computer time this cost. They used a number of supercomputers, and they essentially spent 35 or 36 CPU years on the calculation. Now, 10 years later, progress in computing power had improved so that instead of having a number of professional number theorists with supercomputers, a user of the TI calculator forums, Benjamin Moody, just posted a factorization of a 512-bit RSA signing key for the TI calculators, which he factored in 73 days on a completely normal computer that was just sitting in his basement. Just last year, this was very late last year, another essentially amateur, Zachary Harris, factored the 512-bit email domain authentication keys that Google and a number of other prominent companies were using. In the numbers that he has was that it took him 72 hours for a key, and it cost about $75 of Amazon EC2 time. So this is incredible progress. And I mean, the big, bold moral here is that at this point, an amateur can use off-the-shelf software to factor a 512-bit RSA modulus in about a day for a few $100s, or if they're willing to wait a little bit longer, they can lower that cost even more. So I wanted to test out this assertion, so I tried to do it myself. I hadn't actually used any of these pieces of software yet, but so here's how I did it. I used computing power from the Amazon Elastic Compute Cloud. There's a very nice software package from MIT that lets you, it gives you a nice interface for essentially spinning up a computing cluster of EC2 instances. And then I used an open source number field sieve, a piece of number field sieve software called Cato MFS, which is from a number of, it's a French project, and it's basically an implementation of the number field sieve, which is designed for everyday factoring needs. If you need to factor your 512-bit key, it just has a set of parameters. Everything's arranged for you, so you just hit go on the script and it will do everything for you. You don't have to think about it. So here's some details on my first attempt at factoring a 512-bit key. So it took me 30 hours to factor a 512-bit RSA modulus, which is, for the computers that I was using, it was $234 of computational time. And the amount of time that it took on each step of the algorithm, it took 7 minutes to complete the polynomial selection. That was parallelized. It took 14 hours parallelized to complete the sieving stage. It took an hour and a half on a single core to generate the matrix that I was going to do linear algebra on. And then it spent 14 hours actually finishing the linear algebra. This stage was only partially parallelized. And then the final stage of computing the square root took 23 minutes on a single core. So because I wanted to do this as fast as possible, I just took the biggest computers that Amazon would allow me to use, and I took the maximum number of instances that I was allowed to spin up. So that I had a cluster consisting of 21 8x large compute optimized cluster compute instances, which was, it consisted of 20 spot instances, which the average price was 27 cents an hour to use, plus one control node that was an on-demand instance, which is more expensive because it was actually, it ensured reliability. So this is just me throwing all of the computational power I could from Amazon at the problem. Of course, the process wasn't quite as straightforward as I might have hoped. There were a couple of little snags. The biggest snag that I ran into was that I started the job and had finished sieving, which took 14 hours. And then in generating the matrix, my instances ran out of disk space, and then the star cluster software started crashing. And the way to deal with this is to increase the size of the virtual disk image. But when I did this, then it sort of continuously crashed, and ultimately I just gave up after many hours of trying to fix the problem and restarted the job. So that was a number of hours wasted. And then the second time that I started running, it again crashed after finishing the sieving stage, which is unfortunate. And for some reason, it didn't want to parallelize the linear algebra across 21 nodes, but it was perfectly happy to parallelize across 16 nodes. I have no idea why. So while the software is very nice, it has some bugs. So in total, I ran up an Amazon bill of $550. This is taking into account all of the time that it took me to figure out how to install and configure everything and sort of run some smaller experiments to make sure that everything worked the way I wanted to, and these sort of false starts. So it's not an entirely free exercise, but in all, 4 days of someone who had never done this before, managing to factor a 512-bit key, that's not bad for doing things. So if you wanted to try this yourselves, some, I think, likely improvements that you could make over my time and cost estimates are first, probably you can use, say, more cheaper instances for the sieving stage, because this stage is completely easily parallelizable. Remember that sieving is just like, here's a number, try to factor it. Here's a number, try to factor it. Here's a number, try to factor it. So this stage is embarrassingly parallel. You just hand out ranges of jobs for a siever to do. And so the more computers that you throw at this stage, the more benefit you have without incurring any time cost. And one advantage to sieving as much as possible is that the more sieving that you do in the first stage, the easier the linear algebra step becomes. And so when, if you read any of the sort of big factoring paper results, they always say we over-sieved in order to decrease the size of the linear algebra step. And this is because the linear algebra step is extremely memory intensive and doesn't parallelize as nearly as well as the sieving stage. And finally, sort of, if people are interested in playing with software, one thing I noticed from using at least this particular software is that while you can parallelize the linear algebra steps somewhat, it is not, it doesn't seem to work very well in practice, and it was only using about 15% of the available CPU on each of the instances that I tried. So fixing the implementation or giving proper parameters so that it could best take advantage of the massive amount of computation power in my 620 core cluster that I was willing to throw at it and pay like $7 an hour for could possibly have reduced the time for linear algebra quite a bit. One sort of upshot of this, the big moral here for practice is that this kind of computation lets you understand a little bit better what kind of, what the security of various key sizes are in practice. So there's a paper from last year where several researchers did parts of various kinds of cryptanalytic computations on EC2 they did all sorts of things. They looked at Shaw collisions and breaking DES and brute forcing various things. These are the numbers from their paper for factoring RSA keys. So they completed part of the factoring step for both the sieving stage and the linear algebra stage, and then provided some estimate of exactly what the cost would be to complete the factorization on EC2. So their number for a 512-bit key is within an order of magnitude of what I got. So this is totally believable. And for 768-bit key, which is the largest key that, or the largest key size that has been publicly factored, they estimated that it would take about 2,000 compute unit years, and the estimated cost to finish this calculation in 1 year of calendar time would be $422,000. So this is probably, if you actually wanted to factor a key of this size, it would probably be more optimal to just buy a cluster of for that much money and do it on your own dime. Extrapolating to much larger key sizes gives the somewhat incredible figure of $560 million to factor a 1024-bit RSA modulus, which is still essentially the most common key size that we see in practice. And this number, clearly you wouldn't actually want to do this on Amazon, but this implies that if you had the resources of a government and you could produce special purpose hardware for cryptographic calculations, then it is totally within the range of feasibility for a government or even a large company to factor 1024-bit keys with regularity. And this is without any algorithmic improvements at all. So this is just using what is currently the state of the art in factoring the number field sieve. And there have been a few small improvements over the past couple of decades, but essentially the main idea has been in place for 20 years. And extrapolating to 2048-bit keys, the number is basically out of the realm of feasibility now. So this means that if you want to ask about the security of 2048-bit RSA, we clearly need some kind of major algorithmic improvement in our understanding in order to successfully address a 2048-bit RSA key. But I think the usage of Amazon time as sort of the metric of how much are these keys actually worth is interesting. Even though this costs more than doing this on, say, if you have access to a cluster, it costs more than using that cluster, it's still a useful figure to think about. So I think I'm going a little bit faster than expected, but so the summary of this lecture is that according to the best estimates that we have, it costs $560 million to factor a 1024-bit key if you're doing it on Amazon EC2. So in the next lecture, I'm going to talk about factoring 60,000 1024-bit keys for $5. So that's the end of lecture 1.